We could do a problem just like we did, just like the last one we did with circular cross sections also, where part of the circle comes out above the coordinate plane and the other half comes out below. In fact, if we had circular cross sections for that last example, we would just end up with a sphere, and that would be another one we could do using calculus, or we could just use the geometry formula for it, which would be much easier. But that could be used to check our calculus. The great thing about circular cross sections, you guys know what a lathe is?
Yes.
What's a lathe?
It's like spinning.
But you can use this lathe to create something that has circular cross sections. So if you were to take something off a lathe and slice it perpendicular to the axis that it was rotating on, you would get a circle at that cross section. Does that make sense?
Yeah.
So a lot of what we're going to deal with here are called volumes of revolution. So we're going to take some shape and we're going to revolve it around an axis. If I took this shape, I know it's very poorly drawn, but if I took this shape and revolved it around the red line, I would get something that looks somewhat like a baseball bat. Okay? So we're going to be able to use calculus in the same way we just did in the last example to find volumes of revolution. So we're going to be looking at volumes with circular cross sections. So a solid revolution is just, it's a solid that's created by revolving a region in the plane around an axis. So I want to look at an example here. So if we take this region right here, that's defined by this function. This is actually the square root function, but it doesn't matter that it's the square root function right now. So it's bounded by the square root function, the x-axis, and this line x equals 4. We can take this area and rotate it around really any axis. We could rotate it around the x-axis and we would get a solid. If we rotate it around the y-axis, we would actually get a solid with a hole in the middle. And we'll talk more about those later. But we can get different types of shapes by revolving it around different axes. So what I want to do right now is just kind of get an idea of what this looks like. I want to refresh something. If we were to find the area, or we wanted to find the area of this thing, we started doing that by breaking it up into rectangles and then making the rectangles narrower and narrower and narrower until we got to an integral. We can do the same thing with this, with volumes, just like we did in that last example. So let's just visualize here. If we take one rectangle here, and we revolve that around the x-axis. So we're going to say the x-axis here is our axis of revolution. What we end up with is what? What is that? It's a cylinder, right? What? A drum? Yeah, it kind of looks like a drum. So if we just take that one rectangle and we revolve it around the x-axis, we end up with a cylinder, and we can find the volume of that. We're actually going to call that a disk. And if we make it narrower, which realistically, if we were trying to approximate the volume of this thing, we would make it as narrow as we can. So if we made it narrower, it would look more like a disk than what we would call a cylinder, even though it is still a cylinder. And the volume of this disk is going to be what? How do you find the volume of a cylinder?
34, 430.
A cylinder is just a prism.
Oh, it's just area based on height.
Area of the base times the height, exactly. So in this case, the area of the base is pi r squared because it's a circle, and the height is, we'll call h right now. But really, what are we going to call that height? Delta x, right? In this case, since it has a thickness, we'll call that delta x. And the radius right there, that's going to be the distance between the function and the axis of revolution. Okay, so we're going to call that the radius, and it's going to just be the distance between the axis of revolution and the function itself. And so we want to write that as a function of x. Typically that would be written something like this. You don't need to write that down, but it would be the distance between the function and the axis of revolution. If the x-axis is the axis of revolution, then what would be k here? 0, because y equals 0 is the x-axis, right? All right, so then what we could do is do this with a bunch of them. So what we end up with, our volume of this particular cylinder is going to be pi times the function of our radius squared times delta x. And with this delta x in here, you might start guessing what we're going to do with it eventually. We're going to write it as a Riemann sum and then ultimately an integral, yes. Then we can do this with all of them, all of those rectangles, revolve all of them around the x-axis. It would look something like this, and we get something that looks like maybe the nose of a missile or something like that. And by adding up all of those volumes, we get the volume of the entire solid is this sum right here. And that sum turns into an integral when we let delta x get really, really, really small. Does that make sense? Okay, so let's do an example. So I have the same example that we just went through, the idea of this width. Sorry, that was a little awkward, but you get the idea, I think. But I put some numbers on it. So we have the function y equals the square root of x, and it's also bounded by the x-axis and the line x equals 4, and we're going to revolve that around the x-axis. What I like to do when I'm doing this is kind of draw a picture or draw things in the picture that help me. So I like to highlight the axis of revolution and indicate that's the axis of revolution by drawing a little arrow there. This is just a reminder to me that this is what I'm rotating around. Since I'm finding the volume of this area revolved around this axis, I'm going to start adding things into the picture that are going to help me with that. So let me go back to this here. I'm going to slice it perpendicular to this. So I'm going to take these slices and I'm going to revolve it around the x-axis, and each slice is going to turn into a circle with just a little bit of width. What is the radius of this particular circle going to be? Let's say, and I know I put this at 2, but let's just say this is just at a generic x value, at some x value. So in terms of x, what is this radius here going to be? Did you guys hear what Devin said? Yeah, that's just going to be the square root of x. So the radius of that circle is the square root of x. So then what is the area of that circle in terms of x? It's going to be pi r squared, right? So in terms of x, I can replace the r with the square root of x. So it's pi times the square root of x squared, which is pi times x. So the area of that circle is pi times x. If that circle had a little bit of thickness, let's call that thickness delta x, then the volume of that disk would be pi times x times delta x, the thickness of that disk. This is the formula I asked you to write down yesterday. It says the volume is equal to the integral of the area from our lower limit to our upper limit, and those limits depend on the region. This integral right here is what we get when we take the sum, the Riemann sum, and let the thicknesses go to 0, get infinitesimally small. So if we apply that in this particular case, we can replace the a of x with pi times x. Our limits are going to be from 0 to 4. And then we just have to evaluate this integral. And evaluating that, we get 16 pi over 2 minus 0, or 8 pi.